Hi there and welcome to PhD at Living. Today continues our Mariana's Trench-like dive into the chemistry of atomic weapons, and we are on episode 5. So far we've talked about the theory of nuclear chemistry and how that relates to radioactivity and nuclear fission. We've talked about Enrico Fermi and Chicago Pile 1, the first self-sustaining nuclear chain reaction, and we've talked about how to get enriched uranium and pure plutonium from the separators at Oak Ridge and the reactors at Hanford. Today we're talking about how to get an atomic bomb on paper and turn it into an atomic bomb in real life. And that, my friends, brings us to the granddaddy of all secret laboratories, Los Alamos. A month before Fermi ramped up Chicago Pile 1, a bull of an army general, Leslie Groves, and a scant theoretical physicist from Cal Berkeley, J. Robert Oppenheimer, toured northern New Mexico looking for a place to build an atomic bomb without anybody knowing it. Groves had just finished building the Pentagon and was chosen to lead the Manhattan Engineer District, the Army's component of the larger Manhattan Project, in September 1942. Oppenheimer was tapped to lead the technical side of the atomic bomb a month later in October. Oppenheimer's proposal to Groves included having a central laboratory where work on the atomic bomb could be discussed freely. Without that central lab, progress would be too slow, both because the utmost classified nature of the bomb prevented open discussion and the possibility of redundant work. With the benefit of hindsight, Oppenheimer was an inspired choice. His calm, unflinching leadership, ability to juggle dozens of highly complex scientific concepts simultaneously, and administrative tact in dealing with Nobel laureates and egos of all sizes unquestionably guided the bomb project in a way that no other person, including the revered Lawrence, Fermi, or Compton, could. But let's not kiss his ass too much here either. At the time of his appointment, Oppenheimer was known to be a mercurial goober. During his undergraduate studies at Harvard and grad work at Cambridge and later Göttingen, Oppenheimer was overcome routinely by bouts of madness and depression, but also moments of brilliance not seen by a lot of other folks in his generation. He made friends with Werner Heisenberg, Wolfgang Pauli, Enrico Fermi, and Edvard Teller, but his experimental technique was so poor that theoretical physics was by far the better alternative. Weirdly, Oppenheimer made good friends with Linus Pauling when they were at Caltech together, but Oppenheimer tried sleeping with Pauling's wife. Not cool, bro. As a graduate student at Berkeley in the 30s, Philip Abelson of the uranium hexafluoride synthesis and liquid thermal diffusion separation technique remembers how much tact Oppenheimer, by then a professor, did not have. Oppie, as his friends called him, was aloof and would routinely cut people down in public, Ernest Lawrence included, if he disagreed with the science of their idea. It was entirely besides the point that Oppenheimer was usually correct. Hardly the model of a lab director that could manage egos and ideas with equal discretion. Oppenheimer also treated himself like dirt, chain-smoking like a maniac and wasting away to just over 100 pounds by the end of the war. And yet, as explained by Hans Bethe, quote, he was qualified for that by his very quick understanding of anything. He could understand the gist of an explanation long before the other person had finished his explanation. And he could then draw the conclusions of what to do next until everybody at Los Alamos was conscious that Oppenheimer understood everything much better. And we were very happy to have him as a director." End quote. At any rate, in mid-November 1942, Groves and Oppenheimer chose the Los Alamos Ranch School as the site that would build the atomic bomb. With the lab decided, Oppenheimer's job now was to fill the lab with personnel capable of making the bomb a reality. And so Oppenheimer traveled the United States recruiting dozens of scientists from universities and labs across the country. His pitch went something like Glenn Seaborg's at the Met Lab. I can't tell you what you'll be doing, where you'll be doing it, or for how long you'll be doing it. Also, you have to drop everything and come now, but it could win the war. Are you in? Oppenheimer emphasized the climate, physical beauty, and recreational possibilities of the unknown location you couldn't hear about until you already accepted to put your life on hold and move your entire family. As it turned out, rent at Los Alamos was 7% of one's salary on the low end and 13% of one's salary on the high end. So, not too bad, although if you were single, you probably were staying in a dormitory with about 59 other people, so there was that. And thus began the mass exodus of scientists to 109 East Palace Avenue in Santa Fe, New Mexico. After that, they were given security passes and shipped up to Los Alamos to get to work. Initially, the lab was broken into 5 divisions: A, administrative, T, theoretical, P, physics, C, M, chemistry and metallurgy, and E, ordnance and explosives. The contract between the Army and the University of California to operate Los Alamos was officially signed on April 20, 1943, although it was backdated to January 1st because work was already rapidly occurring. In fact, 5 days before the contract was signed, Oppenheimer's assistant, physicist Robert Serber, began to explain the physics of atomic weapons to the arriving scientists in a series of 5 lectures. Notes from these lectures were eventually written up into a small book known as the Los Alamos Primer. When debating possible bomb designs, 2 were chosen. Coded by Serber as Thin Man and Fat Man, so the uninformed would think FDR and Winston Churchill, not war-ending weapons. Thin Man would be a gun-type device using either plutonium or uranium as the fissile material. Fat Man, on the other hand, would be an implosion-type bomb that would use only plutonium as the working stuff. We'll get there in a bit. Early in the game, the scientists were less than optimistic about their chances. Here's Vannevar Bush, head of OSRD, after a meeting to discuss the game plan. Quote, "Even if the physicists get all that they expect, I believe that there's a very long period of engineering work of the most difficult nature before anything practical can come out of the matter, unless there is an explosive involved, which I very much doubt." End quote. While the lab had a fair focus on where the research needed to go, agility and flexibility were paramount. Similar to his approaches with Oak Ridge and Hanford, Grove's plan for Los Alamos was one of options. Quote, "There's no objection to a wrong decision with quick results. If there's a choice between 2 methods, one of which is good and the other looks promising, build them both." End quote. What a refreshing idea. I'm a big proponent that quick and wrong is not usually bad. I spent so much time failing in grad school that negative results are almost always good things to me. At least then you know it wasn't going to work and you can stop worrying about it. With that as a historical foundation, here's the scientific end goal: a fast neutron nuclear chain reaction that created enough energy to destroy a city before it blew itself up. Here's a small list of things that needed to be solved before that goal could be reached. Would uranium emit neutrons fast enough to propagate a fast neutron chain reaction? Maybe. Would plutonium emit neutrons under fast fission? Hopefully. Would plutonium emit neutrons fast enough to propagate fast fission nuclear chain reactions? Also maybe. How much was a critical mass of uranium? How much was a critical mass of plutonium? Less than uranium? How much was a working mass of either element? No idea. How did uranium and plutonium act as metals, much less fissile materials, at the temperatures and pressures we were looking at in the bomb? I don't know. Would any of this actually work? Look at my previous answer. What's your record for consecutive questions asked? 38. At the risk of making this already really hefty series even more pedantic, I'll spare you all the gory details and just throw this superlative out there. This was the single greatest scientific achievement of all time, so just assume every step along the way here was achieved arduously and not in a straight line. With that, let's go! Unlike a slow neutron nuclear reactor, our fast neutron atomic bomb was designed to release its energy ludicrously fast. So fast, in fact, it might accidentally kill itself. There are 2 competing factors in this process. First, there's the time it takes to make a fission happen. A speeding neutron comes in and smacks either U-235 or Pu-239 and makes it blow up. How long does that take? Part 2 to that particular part 1 is, once that happens, how long does it take for another neutron to come out of it to start another fission reaction? Second, we know crazy amounts of energy are created when a fission occurs. Uranium and plutonium, being after all real-life metals, will expand when heated. Thus, that increases the distance a neutron has to travel before it can initiate another chain-propagating fission reaction. This means the fission chain reaction had to propagate faster than the uranium or plutonium would expand due to the heat of the fission chain reaction. If the fission chain reaction was too slow, the uranium and plutonium would expand themselves so much that it would significantly reduce the yield of the bomb. A lot of this is physics, and I'm just a little chemist, but in July 1943 it was proven plutonium does in fact emit neutrons upon fission, and it emits more than uranium. It was also proven that U-235 emits neutrons in nanoseconds, meaning there was plenty of time for the chain reaction to proceed before the uranium expanded itself apart. Okay, now that we knew the critical mass wouldn't blow itself apart before the fission had time to make bomb-worthy energy, we had to find out how big the critical mass was. For both the theoretical and experimental divisions at Los Alamos, the critical mass of uranium and plutonium were the most important numbers obtainable. They would determine the final size of the bomb and even whether it could be carried by a B-29. Frisch and Perels hinted at this number for uranium in 1940, but betting the performance of an atomic weapon on a calculation with a number of assumptions was a little bit too risky for Groves, Bush, and Conant to afford. Tons and tons of calculations and experiments were done to estimate the critical mass of plutonium and uranium, but the best they could do was approximate to the real thing. After all, if you made a real critical mass of either material, you'd release untold amounts of energy and probably kill everybody in the room. But, what if you could make a critical mass for just like a microsecond and see what happened? Well, that'd be irresponsible. The margin of safety for an experiment like that would be razor thin, and if one little piece of it went wrong, the whole thing would go really, really wrong. Yeah, but think of all the data. As it turned out, the man responsible for the theoretical calculation of critical mass was also integral in the experimental measurement of it. Otto Frisch had found his way to Los Alamos on loan from the British and was already working on critical assemblies of uranium-3 hydride when he proposed that very experiment. Uranium-3 hydride had been used previously in not-so-crazy criticality experiments. The great part about this material is it's a nuclear fuel and moderator all wrapped up in one. The very low atomic weight hydrogens did a great job at moderating neutron speeds from uranium fission. The problem with uranium hydride is it's a nuclear fuel and moderator all wrapped up in one. If you got too much of this material too close together, it could make a critical mass itself. For example, one time Frisch leaned against a table and the hydrogen in his body was enough to make a pile of uranium-3 hydride go slightly critical for a couple seconds. With that as a treacherous background, Frisch wanted to make a just barely subcritical assembly of uranium hydride shaped like a donut. Then he would make a second piece of uranium hydride like the donut hole and drop it into the hole of the donut. This would make the mass go slightly critical, but only for as long as the falling donut hole was actually in the hole of the donut. Frisch was essentially making an atomic bomb for a few fractions of a second. Needless to say, if something in this experiment went wrong, it would go really, really wrong. For that reason, Richard Feynman named this experiment Tickling the Dragon's Tail. Feynman unfortunately gets left on the cutting room floor here because there's just not enough time that he deserves to have devoted to him. That said, his life is a masterclass. His autobiography, Surely You're Joking, Mr. Feynman, is a hilarious, enthralling detail of a brilliant scientist's life. He goes in depth in the book about his time at Los Alamos during the war years, and he has stories like how he would pick his co-workers' classified safes locks and memorize their combinations for fun. Great stuff, you gotta check it out, but Dragon Tales. The Dragon's Tail experiments established a lot of previously unknown fission parameters, but the most important one is it proved that the atomic explosion would work. Absolutely, unequivocally, would work. In one experiment, the temperature rose 6 degrees C in 3 milliseconds and was dubbed a nuclear explosion nipped in the bud. To the highest degree of scientific certainty possible, the data collected and calculated suggested uranium and plutonium would fission as intended in a bomb. The challenge now was definitively putting those materials in that situation and making the bomb. Finally, after like 4 hours of this, we are at the bombs. Let's talk about the gun bomb. A gun-type bomb has a propellant charge and a piece of fissile material, uranium or plutonium, but for the sake of argument here, let's just say plutonium, at one end, and a second piece of fissile material at the other end of the gun. When the propellant charge burns, it creates gas, the gas creates pressure, the pressure pushes the first piece of fissile material into the second piece. This creates the critical mass, which fissions like a boss and blows up. This whole setup is pretty similar to a regular gun, except the target is also inside the gun. Also, this particular gun blows up a city instead of, like, delivering meat to the table. The simplest type of gun bomb has two hemispheres that get smashed together and create the sphere. With a margin of error built in to make sure the gun worked, however, the Los Alamos scientists wanted more than 2 critical masses of material. For the half-spheres, this is a problem because one or the other or both of them would be more than one critical mass themselves, and more than one critical mass can make a critical mass can make a chain reaction, so that probably wasn't the best idea. What was eventually decided upon was a hollow cylinder at one end and a rod cylinder at the other. This way, the rod would connect with the hollow cylinder and complete the cylinder. Also, even though the open cylinder has a critical mass higher than 1, the geometry of this prevents any stray neutrons from creating a chain reaction prematurely. For almost 50 years, though, outsiders of Manhattan got wrong which piece was the bullet and which piece was the target. Folks had always just assumed that the hollow cylinder would be stationary and the rod would be fired into it. In reality, in Little Boy's setup, the rod was stationary and the cylinder was fired over it. In one of the craziest stories of the post-Manhattan world, a guy named John Coaster Mullen, a truck driver and atomic forensic researcher in his spare time, can't make it up, discovered that fact. Crazy story, link in the description. We could go on and on about the construction of the gun bomb, but the main concerns were primarily engineering in nature, and this, after all, is a chemistry channel. I'll summarize and say that the gun bomb was a unique engineering endeavor because it only needed to be used once, but it required extremely accurate ballistic trajectories and had to fall 20,000 feet from an airplane without breaking apart or significantly veering off course. Because of the obvious impracticalities of using real atomic bombs or even full-size surrogates as tests, the gun team had to scale down their experiments. After the ballistic and metallurgical questions were answered, any future experiments done were, well, from a chemistry standpoint, pretty ho-hum and only served to increase the confidence that the gun bomb would actually work. But wait! This is science, baby, and it don't ever work that easily. For a couple years, the big names at the Met Lab in Chicago, Fermi, Seaborg, etc., had bandied about the idea that spontaneous fission in reactor-bred plutonium could be bad news for the plutonium gun bomb. Cyclotron plutonium, which was all we had up to early 1944, had a completely acceptable spontaneous fission rate. But the insane neutron flux at the reactors at Oak Ridge and Hanford may create new, as yet unidentified species in the plutonium. Even with those concerns, most people pushed it to the back of their minds and dismissed it as being from any chemical impurity in the plutonium that could be easily separated by Seaborg's extraction processes. Well, in April 1944, a sample of reactor-bred plutonium from Oak Ridge was delivered to Los Alamos. At Los Alamos, Emilio Segri immediately got to work measuring spontaneous fission in the Oak Ridge sample, and found a grave impurity. The massive problem is the impurity in the plutonium was plutonium. 2 minutes. While plutonium-239 is the good working isotope in an atomic weapon, it was discovered plutonium-240 existed in reactor-bred plutonium and had a completely unacceptably high spontaneous fission rate. What this means for the gun bomb is as the pieces are approaching each other, plutonium-240 would be spontaneously decomposing, spontaneously fissioning. What's a product of plutonium fission? Neutrons. As the pieces were coming together, the Pu-240 would be spitting neutrons all over the place, which eventually would make a critical mass before the pieces had time to fully assemble. This critical mass before full assembly is known as a pre-detonation or a fizzle and dramatically reduces the effective yield of an atomic bomb. The only way to get around this at this point was to separate the Pu-240 from the Pu-239. And as we know from uranium, that is an impossibly difficult thing to do, and this late in the game, there's no way they would have been able to separate enough Pu-239 in time to win the war. In layman's terms, long story short, plutonium would not work for the gun-type bomb. Segri's experiments were resoundingly confirmed, and on 17 July 1944, Oppenheimer, Conant, Compton, and Monsanto's Charles Thomas discussed and then met with Groves, Nichols, and Fermi for the final decision. Thin Man was dead. Luckily, all was not lost. The gun bomb would still work with uranium. Additionally, because a critical mass was easier to initiate in uranium than plutonium, the uranium gun bomb could be smaller. Hence, all the work from the plutonium gun bomb was easily transferred to uranium, and Thin Man became the less complicated Little Boy. To get the good pure uranium for the bomb, chemists at Los Alamos had to reduce the material from its Oak Ridge hexafluoride state back to zero valent metal. Chemist Richard Baker achieved a 99.96 recovery rate. My grad school advisor used to say people either did or didn't have a green thumb when it came to organic chemistry. This was usually a nice way of letting me down when everything I touched turned to hot garbage. But I digress. If some people have a green thumb at organic chemistry, Richard Baker is Captain Planet. With that good pure uranium, scientists made the open discs for that hollow cylinder projectile and the rod targets. Progress was so good on Little Boy that in October 1944, a full 10 months before Little Boy's deployment, James Conant wrote the backhanded compliment, quote, "Indeed, the gun method seems as nearly certain as any untried new procedure can be," end quote. There are other fairly important components to the gun bomb like a tamper or the initiator, but we'll hit those pretty heavily in the implosion bomb. Change the configuration just a little bit and you've got everything you need for Little Boy. The other chosen bomb design, Implosion, was, how should I say this, way more complicated in a bunch of different ways. Thin Man got the majority of research at Los Alamos well into 1944, and Fat Man was put on the back burner as more of a side project. Caltech physicist Seth Nettermeyer was the main, and let's be honest, probably only proponent of the implosion design and was the implosion group leader. While implosion was debated quickly during the early primer days at Los Alamos, it wasn't really looked at seriously until it became the only option for utilizing plutonium. Implosion got a big boon in September 1943 when the legendary John von Neumann, Hungarian polymath who mastered calculus by the age of 8, knew more about Byzantine history than a professor of Byzantine history at Princeton, spoke at least 4 languages, wore a 3-piece suit on a mule down the Grand Canyon, got in plenty of traffic accidents because he would read books while driving, yes, and also came up with some of the most important mathematical concepts of the 20th century. Performed some serious calculations that supported the implosion device and showed that a larger high explosive to plutonium ratio would require both less plutonium and less pure plutonium than the gun-type bomb would. This, coupled with the convenient lack of any other option for plutonium in the summer of 1944, really helped to exponentially increase both the size and priority of implosion research. Nettermeyer laid the foundations for implosion research and was a fine scientist in his own right. However, from the accounts that I read, Nettermeyer just didn't have the managerial chops required to have hundreds of people working under him. Slightly before the fateful July decision to reorganize the entire lab's focus on the implosion bomb, Nettermeyer was replaced by Harvard chemist George Kistakowski. In that reorganization, Oppenheimer created 2 new divisions: X Explosives Division under Kistakowski and G Gadget Division under Robert Bacher. Kistakowski's task was to make the implosion bomb a reality. Bacher's group would then test a full-scale version of that implosion device. Critical Assembly summarizes implosion research thusly, quote, "The history of the 7-pronged experimental program to study implosion during World War II is one of painstaking progress, with few highlights or definitive measurements, many ambiguous steps, and numerous failures," end quote. Sounds like my time in grad school. Heyo! Here's the plan with the implosion weapon. A subcritical piece of fissile material would be smashed together from all sides to create a supercritical mass. The advantages to Fat Man were many. Because the design was more efficient, less fissile material could be used. In addition, more energy per unit plutonium would be gotten out. And because the mass wouldn't go critical until the bomb had already detonated, Fat Man was inherently safer than Little Boy. The disadvantages to the implosion weapon, however, were every bit as daunting and then some. Somewhere around 6 kilograms of pure plutonium was needed to make the bomb work, and at this point we only had micrograms of it. To put it in perspective, in the first physics experiment at Los Alamos in July of 1943, Enrico Fermi was using indium foils to measure secondary neutrons on fissioning plutonium-239. He was using a sample that was 200 micrograms, all of it gotten from Glenn Seaborg at the Met Lab in Chicago. That represented the majority of material in the world at the time, so we only needed to increase that amount by 30 million times before there was enough plutonium for a bomb. Also, the metallurgical and chemical properties of plutonium metal were needed before accurate assembly could occur. Also, imploding a plutonium core spherically in perfect synchronicity had never been attempted before, much less achieved. Many problems here. Also, initiating the device to ensure there were enough neutrons around to start the chain reaction was completely non-trivial. Which brings us to George Kistakowski. Ukraine-born and trained in Germany, Kistakowski joined Harvard in 1930 and became a U.S. citizen in 1933. Quick rehash history lesson. When he created the National Defense Research Committee in 1940, FDR tapped Vannevar Bush to be in charge of the whole thing. Bush, who founded the company that eventually became Raytheon, took James Conant, then president of Harvard, and put him in charge of Division B, which was responsible for, among other things, explosives and propellants. Conant, drawing from his own talent pool, pulled Kistakowski in to be in charge of Section A1's explosive research. A year later, the Office of Scientific Research and Development is created. Bush goes in charge of that. Conant becomes in charge of what's left of the NDRC, and Kistakowski is pulled up to Division B. Eventually, Division B spun off, and Kistakowski is left with just the explosives and propellants. As I'm sure you know, I'm an explosives guy through and through, which means we're taking a slight detour, but I promise we'll come back. Kistakowski was not terribly impressed with the US's knowledge base of explosives in the 1930s and set about to change that. Kistakowski's nickname, was a proponent of the improved synthesis of RDX, which was the topic of my very first video on this channel. Kistakowski also continued good research into shock physics, where he noticed some differences in his work compared to pure Chabin-Jouguet theory. Finally, Kistakowski was interested in shape charges, which brings us back to the Manhattan Project, just like I said it would. Kistakowski's job was to make the implosion device a reality. Working generally from the outside in, to do that, we needed reliably uniform explosives to simultaneously compress the plutonium core, reliably precise detonators to make sure the explosives all fired at the same time, a good tamper material that not only reflected neutrons back in, increasing yield, but also kept the mass solid for as long as humanly possible, the plutonium core. Enough said. And finally, a good initiator that would spew neutrons like crazy to ensure the reaction happened. This is, per usual, a gross oversimplification of an implosion bomb, but it gives you a working understanding of the science. With that, on to the explosives. With the explosives, the challenge was to get a mass of them to detonate spherically and compress the plutonium core in every direction. The problem is that explosives detonate spherically. How's that a problem? Aren't we detonating a sphere? They do, but we're detonating it from the wrong side. If you have a single detonator here, the wave will propagate like this in a spherical direction and sort of just push everything off to one side. With a second detonator at 180, we get a second wave like this that kind of pushes everything like a sandwich, and we get coming out the sides. With 4 detonators at 90 degrees, you have this sort of shape. So you just keep adding detonators around the outside until you get a shape that compresses everything spherically. Except that's not how it works at all. No matter how many detonators you put around this ring, you will never get a spherical compression. There will always be some sort of jet or squirt or something that messes up the spherical assembly. So how do you fix it? The solution is to invert the detonation. We had to fundamentally change the shape of the explosive shock wave from detonating spherically this way to detonating spherically this way. This entire branch of explosives is called shape charges, which, as the name suggests, are charges of explosives whose shape causes the detonation wave to move in a given geometry. As an example, RPGs are probably the best known shape charge, as they take a copper cone and invert it into a ludicrously fast metal bullet that pierces through almost anything in its path. During World War II, though, we were just learning that you could do this sort of thing with explosives, so this is another piece of the Manhattan Project that's basically a new frontier. Much like an optical lens bends light by slowing it down, so would an explosive lens do for the shock wave in Fat Man. This required combining the theory of shape charges with 2 explosives with different detonation velocities. A fast explosive on the outside would initiate the implosion, and then the shock wave, when it reached the slow explosive, would invert, making that spherically compressing wave for the bomb. This is great and all, but how do you make explosives into pretty shapes? Well, like making a big ice cube, except with really dangerous water. Instead of machining blocks out of solid explosives, it was much easier to pour a liquid explosive into a mold and then solidify it. Conveniently, we knew trinitrotoluene, more appropriately 1,3,5-trinitro-2-methylbenzene, but TNT just sounds so much cooler, had this really awesome behavior of being a stable liquid explosive above 80 degrees C. This meant you could melt it with steam, pour it into whatever mold you were using, and then solidify it into a block. Also great is you could add other explosives to the TNT while it's liquid. Composition B, one of the workhorse explosives of World War II, was 60% RDX, 40% TNT. Or you could use penolite, 50-50 TNT PETN, or octol, TNT HMX, or amatol, TNT ammonium nitrate. The list goes on. Kistikowski said the melt casting process created a thick pea soup-like solution that had a characteristic TNT smell. Probably not unlike napalm in the morning. The worst part of melt casting was the end. Density changes when things solidify, so the charges had a habit of slumping in the middle because that's what cooled last, or they would create little air pockets and voids. Those voids would drastically mess up the detonation wave speed in the explosive lens, so they weren't usable. Kistikowski summed it up, quote, "Well over 20,000 castings were delivered to the firing sites, while the number of castings rejected because of poor quality or destroyed for other reasons is several times that figure," end quote. At its peak, Kisty's group was going through over a ton of explosives per day. As important as getting good castings was for implosion, getting the right combination of fast explosive and slow explosive was equally important. That way the shockwave could be sufficiently slowed and shaped to create that compressing sphere. For the degree of accuracy needed for Fat Man, really accurate measurements of detonation velocity of each explosive were needed. Instead of spending time getting accurate detonation velocity measurements from theoretical scenarios, the scientists at Los Alamos got empirical data in relevant environments. In keeping with the spirit of the Manhattan Project, who cared why it worked as long as it actually worked? The most accurate method for measuring detonation velocity was the electric pin method. Basically, you'd get your charge of high explosive and you would put electric pins at given distances down the charge. Those pins would all be hooked up to an oscilloscope. When the explosive charge was fired, as the shockwave came by and destroyed each electric pin, the oscilloscope would get a reading. Then you could basically just take all the times of the pins as they got fired and broken, and the distance between the pins, because you know the distance, you're the one that put the pins in the daggone charge, and even I can do this math, distance over time equals velocity. The nice part about the electric pin method at Los Alamos is it could be done three-dimensionally, so you could put pins all along a spherical charge and see how the shock wave was propagating in 3 dimensions. Remember that 2,000 pounds of explosive Kisty was going through every day? Yeah, it led to the choice of Composition B, 6040 RDX TNT, being chosen as the fast explosive for the lenses. Along the way, PTX2, Pentolite, and Torpex were used. PTX2, a mixture of RDX, PETN, and TNT, Pentolite, as we've said, a 50-50 mix of PETN and TNT, and Torpex, usually used by the Navy for torpedoes, in a 42-40-18 mixture of RDX, TNT, and powdered aluminum. My guess is, with the PETN nitrate ester in both the Pentolite and the PTX2, that nitrate ester didn't hold up so well thermally under the hot melt casting environment, so that's why those ones weren't used. Fun story, Kistikowski's Ukrainian accent led to everybody at Los Alamos, instead of saying pentolite, said pientolite. And for the slow explosive, baritol, a mixture of aluminum, TNT, barium nitrate, nitrocellulose, and stearoxyacetic acid. I went online and looked it up, couldn't find much on it. It was probably used at well less than 1%, so it doesn't really matter. Was chosen. Which brings us to our combination explosives lenses. We have Comp B, the fast explosive detonating at 8,000 meters per second, and baritol, the slow explosive detonating around 4,800 meters per second. Super! Now we know the identity of the fast and the slow explosives, and we have a pretty good idea how to make the shape charges necessary to create the shockwave implosion. Now the problem was figuring out the best configuration and shape. Initially, both X-ray and optical photography were used to determine the effectiveness of symmetry experiments on cylinders instead of spheres. The cylinders were easier to analyze. A third metric was terminal observation, which is science speak for saying they looked at the blowed up pieces of the cylinders. I only jest a little bit, because analysis of post-blast chunks is actually a pretty darn decent way of determining the effectiveness of a given explosive, directionality of blast, and even if an event is high order or low order. Many of the first symmetry experiments were not great because the symmetry wasn't working. There were significant jets, that is, squirts of metal that came out of what was supposed to be the symmetric implosion, or spalling, which is shearing of pieces off the surface when the detonation wave hit the surface and reflected back. Up to the summer of 1944, Kisty's division got significantly better at identifying and elaborating on the problems. It did not, however, get any better at fixing the problems. They tried using really slow explosives, they tried putting inert pieces of wood between charges, and they even tried more initiation points. Nothing worked. Because things were going so poorly, in a proposed plan of November-December 1944, Kisty wrote as a final summary, quote, "The test of the Gadget failed. Project staff resumes frantic work. Kistikowski goes nuts and is locked up," end quote. In order to expedite learning and minimize consumption of energetics, Kisti broke the division down into 3 groups that would get extensive experience with small-scale shots before committing their resources to large-scale shots. In this way, the less promising methods of implosion would be eradicated well before the real time and money were spent. A bright ray of sunshine in an otherwise nearly endless string of cloudy days was an extremely valuable series of experiments called the RaLa Experiments. Named for the radioactive lanthanum used as a source, the RaLa experiments were conceived by Robert Serber and tested the implosion efficiency of the explosive lenses designed by George Kistikowski. Here's how it worked. A small pit of radioactive lanthanum-140 was put inside the center of a larger metal sphere. Usually this was cadmium metal because of its density and opacity to gamma rays. Then the explosive lenses were put around it and detonated. Ionization chambers measured the gamma emission from a number of different points around the sphere, and if the traces of gamma emission were similar enough on those ionization chambers, that meant the explosive lenses were detonating symmetrically. Okay, that's how it worked, but now here's why it worked. Lanthanum-140 is an excellent gamma ray emitter, like super excellent, and gamma rays have much higher penetrating power than alpha particles or beta particles. Because the gamma rays could find their way through the detonating explosives and compressing metal sphere, the scientists at Los Alamos could see what was happening deep down in that spherical configuration. Why specifically lanthanum-140? It turns out it's a beautiful decomposition product of barium-140, which itself is created in mass by uranium fission. For those of you who've memorized the periodic table, you'll see lanthanum-140 is a simple beta-minus decay away from barium-140, converting a neutron into a proton. A huge amount of material and a huge amount of gamma rays. A match made in oddball radioactive heaven. Chemists at Oak Ridge would extract the barium-140 from the uranium junk and set it in lead-lined containers on trucks non-stop to Los Alamos. The scientists at Los Alamos were originally going to leave the lanthanum and the barium together, but Luis Alvarez, who'd been put in charge of the project in April 1944, decided to separate the two. This served 2 big purposes. First, by keeping residual barium-140 around, you'd eventually have more lanthanum-140 for testing. Second, it prevented the test site from being contaminated for too long. Lanthanum-140's half-life is just over 36 hours, while barium-140's half-life is 12.5 days. And as it turns out, strontium-90, another decay product, has a half-life of 29 years. Fortunately for the chemists in group C4, C4, oh yeah, so funny, ha ha ha. Separating the lanthanum from the barium and the strontium was pretty straightforward. Unfortunately, they had to do this as soon as the sample arrived from Oak Ridge, and that usually was very, very early in the morning. Also, sometimes iron contamination caused lanthanum phosphate to gel out of the solution. Whoops! An unfortunate side effect of lanthanum-140 being such a good gamma emitter was its danger. Here's chemist Rod Spence on the lanthanum point sources. Quote, "No one ever worked with radiation levels like that before, ever, anywhere in the world. Even radium people normally deal with fractions of a gram, fractions of a curie," end quote. The RaLa sources were often spewing 100 curies of radioactivity. For comparison, a millicurie can sometimes be fatal. Therefore, these dudes doing the RaLa experiments were working with 100,000 times a potentially lethal dose of radioactivity on the daily. Because of the radioactivity, Alvarez designed the RaLa experiments to be performed in mobile labs made in M4 tanks. It's basically the equivalent of the Breaking Bad Winnebago, except 100 curies of radioactivity is way more dangerous than a meth lab, and also they were freaking tanks. Fortunately, the radioactivity was not as bad as anticipated, so the mobile labs were broken down and turned into a more permanent solution. Even still, boss idea. With all that lanthanum-140 spitting out all those gamma rays and the detonating mass, we needed something to measure it all. An ionization chamber. The basic setup of an ionization chamber was 8 cylinders, I know there's only 3 here, filled with compressed argon and CO2 gas. There were also wires running through the cylinders, such that when the gamma rays came into the tube, they would ionize one of the gases. That was registered as a change in current by the wire in the tube, and then you could read that on the ionization chamber. 4 of these ionization chambers were set up in a tetrahedron for every RaLa test. They would be destroyed in every test, but the chambers were placed far enough away that they could record data before being destroyed. The beauty of the RaLa experiments was twofold. First, you could see the inside of the device, so you would know how the sphere was compressing. Second, it was a continuous test, so you could see the entire event, up till the ionization chambers blew up, that is, instead of just getting a snapshot in time or looking at the wreckage afterward. Like almost everything with Fat Man, Kistakowski's group needed every single second they could to get the final explosive lens design figured out. The final configuration was a series of interlocking pentagonal and hexagonal blocks that resembled something of a soccer ball. Here's a side slice of what one of the lenses would look like. You have the detonator on the outside, a section of the Comp B fast explosive, followed by a conically shaped piece of the slow exploding baritol, then another piece of Comp B fast explosive, and then plutonium core stuff. Here's how it worked. The detonator would fire and the fast Comp B would start detonating with this characteristic shockwave. Eventually, the middle piece, the fastest, would reach the baritol cone first and start slowing down. This would give the edges time to catch up and eventually invert our shockwave. When it got to the second piece of Comp B, the wave was sufficiently inverted, and its purpose was not to change anything about the shape, but because the shockwave had just gone through the baritol and slowed down, the second piece of Comp B was to speed it up and increase the efficiency of the implosion. With a symmetrically compressing detonating wave, we were one step closer to Fat Man being a reality. Concurrent to all of Kistakowski's explosives lens work, and in addition to his RaLa experiments he was already doing, Luis Alvarez was put in charge of improving detonator accuracy and precision. Having perfectly pristine explosives lenses wouldn't matter if we couldn't get them to all detonate at the same time. Here's the problem. Remember, Comp B's detonation velocity is 8,000 meters per second. This means the shockwave travels 8 meters every single millisecond. For Fat Man to fit in a plane, it'd have to be significantly smaller than 8 meters wide, so the detonation wave would travel the entire length of the bomb in well less than a millisecond. Current state-of-the-art detonators in 1944 were blasting caps, basically a wire with a primary and a secondary explosive. Current would pass through the wire and initiate the primary explosive, which would initiate the secondary explosive, which would initiate your main charge. The problem with blasting caps is their tolerances were at least a millisecond, if not multiple milliseconds. If I tried to simultaneously initiate my Fat Man device with blasting caps, and they were off by only 1 millisecond, the shockwave would be 25 feet ahead of the second one before it even fired. Even perfect explosive lenses couldn't overcome that kind of variability. For that reason, we needed a significantly more precise detonator. Enter the Exploding Bridgewire, or EBW detonator. The EBW was invented at Los Alamos by Luis Alvarez and proved out by Larry Johnston, the only person to see all 3 atomic explosions in 1945. The EBW works by passing a huge amount of current from a capacitor into a very small wire very quickly. This causes the wire to boil, so what was previously a pretty small volume of solid is now a huge volume of hot pressurized gas. This creates a shock wave that the explosive has no chance to resist, so it starts detonating and sets off the main charge. While this sounds pretty close to a blasting cap, and it is, there are 2 critical differences to the EBW. The first is the capacitor sends the current to the wire in an extremely precise, repeatable way. This means 2 EBWs could be fired simultaneously within a couple microseconds instead of a couple milliseconds. The second thing, you'll notice there's no primary explosive here. The shockwave created by the EBW is strong enough that you can use a less sensitive, more stable secondary explosive. This makes the EBW inherently safer than a blasting cap. The first test of an EBW is an exercise in elegance. Johnston taped a foot of primacord, basically just packed PETN in tubing, to a 2x4 with a piece of lead underneath. Then he put an EBW at each end. In theory, he fired the EBWs at the same time. They would meet directly in the middle of the foot of primacord. He could then take a measurement off of dead center and see how close the timing was. After the experiment was run, Johnston measured the distance, and it was 1/8 of an inch off of center. This 1/8 of an inch correlated to a 1 microsecond delay. With further improvements and refinements, Alvarez's team was able to get the delay down to nanoseconds. Because the EBW operates in about 1/10 of a microsecond, that means the detonating shockwave moves about a millimeter, not 25 feet. That degree of precision was plenty to adequately compress the core in Fat Man, and that's what the scientists saw when they started using EBWs in RaLa experiments. You see how I brought that full circle? Love that! Moving inward, our next multi-layer piece is the Tamper. The Tamper served 2 purposes. First, it reflected neutrons back into the core while it was fissioning, an artificial way to lower the critical mass. It also kept the plutonium core from blowing apart as quickly as it otherwise would have, increasing the yield. Good materials for the tamper were gold, tungsten, rhenium, or uranium because of their high densities and solid metallurgical properties. The first layer of the tamper was natural uranium, so 99% U-238. On top of that was a real thin layer of boron-10, a potent neutron absorber that was there to make sure no spare neutrons got into the core and messed anything up before operation. On top of the boron was a layer of aluminum metal. This helped to smooth out any of the rough edges from the detonating Comp B and helped to settle the density mismatch between Comp B and the uranium tamper. The aluminum also caused a reflecting wave outward, increasing pressure and compression and yield of the core. Next we have... Actually, shoot, that's it. Boy, that was really easy. Feels kind of weird. Anyway, moving on. Next is the working material of Fat Man, the plutonium core. It seems a little foreign for a synthetic material, but plutonium, being a real live metal, is held to the physical and chemical constraints therein. For example, plutonium has 6 allotropes, more than any other metal. What's an allotrope, you say? Good question, and one I've answered in regard to carbon. Feel free to check it out. There are large density and volume changes in plutonium when it's heated and cooled, so thermal stabilization is needed so it doesn't, crack or go critical and blow up the airplane it's on. Also, the scientists had a hard time figuring out what the real density of plutonium was because they could never get it pure, and chemical impurities were causing the wrong allotrope to be stable at room temperature. Also, the scientists always assumed that plutonium had a higher melting point than uranium. Turns out the melting point wasn't even tested at those temperatures until basically somebody did it accidentally and discovered, in fact, plutonium had a lower melting point than uranium. Let that be a lesson to you, young chemists. Keep in mind that during all this experimenting, the plutonium couldn't just be wasted or thrown away. With failed or successful experiment alike, the plutonium still had to be mercilessly recovered. I'm talking off chem wipes, spatulas, fume hoods, operator clothing. The recovery group did an absolutely stupid amount of work to make sure no plutonium went to waste. And I mean like no plutonium. They had a flowchart designed to separate the plutonium from every other element on the periodic table. And when I say every other element, just look at this thing. Back to metallurgy. Because Fat Man was going to see a large range of temperatures and pressures, the plutonium had to be thermally stabilized. Turned out the best thing to alloy the plutonium with was gallium, because the gallium locked the plutonium into the delta allotrope, which is like totally the best one. Seriously though, the gallium-plutonium alloy was stable over a 500°C temperature range, had a very low coefficient of thermal expansion, didn't corrode easily, and cast well. Check, 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 and check. The plutonium that was used in the Trinity test and Fat Man bomb was alloyed with about 3 mol% gallium. For a good long while, a hollow sphere of plutonium was the design of choice because it had higher efficiency and initiated itself more easily. Unfortunately, it also required higher accuracy implosion, and it was tough enough to blow up plutonium as it was. Theoretical physicist Robert Christie, who was working at the Met Lab in 1942 and just so happened to be present when Chicago Pile 1 went critical, proposed using a solid subcritical sphere of plutonium that would become critical 4 times over when compressed by the implosion. This innovation led to the solid sphere of plutonium being called a Christie pit, and the gadget in which it was used the Christie Gadget. With the many advantages of the plutonium-gallium alloy, its main disadvantage was oxidation. After a number of cores were made, people noticed they tended to oxidize pretty readily. To fix this, a solution of nickel was plated on top of the outer surface, but unfortunately that blistered because the solution got trapped between the nickel metal and the alloy. To fix that, the blisters were filed away and filled in with gold. Yes, gold. The gilded atomic bomb was ready. Alrighty folks, now we have perfect explosive lenses and can perfectly detonate them perfectly spherically with our perfectly optimized tamper and perfectly thermally stabilized plutonium pit. But, the Christie pit did have one significant disadvantage. It was way less efficient than a hollow sphere. For that reason, extra neutrons would be necessary to ensure the fission happened as planned. The solution here was basically an EBW of neutrons, also known as a neutron initiator. This gigantic source of neutrons would make sure the plutonium pit went critical when the fission was supposed to happen. This part of the Fat Man work was dubbed the Dayton Project and happened coincidentally in, against the odds, Dayton, Ohio. The neutron source for Fat Man was a beryllium-polonium initiator. This well-known setup had been used for some time in nuclear physics to create an insane amount of neutrons, and here's how it worked. Polonium-210 is a natural spontaneous alpha emitter, so it would spit the alpha particle, a helium nucleus, 2 protons, 2 neutrons, and decay into the very stable lead-206. That alpha particle would then strike the beryllium-9 and get absorbed, becoming carbon-12, the basis for all life on the planet, so probably a stable atom and a neutron. And that's how our initiator would create the neutrons for Fat Man. Boy, this nuclear chemistry stuff is cool, right? It's kind of like a murder mystery. You're not sure where it's going to end up, but when it gets there, man, is it good. This system is all well and good, except for the fact that polonium didn't exist in a pure enough form and in enough quantity to matter, so extraction methods were required. Monsanto's Charles Thomas was put in charge of this part of the project to make sure there was enough polonium for the initiator. And also organizing plutonium production around the country, but who's counting? At one point during this work, Thomas purified polonium on his mother-in-law's tennis court. Keep that one in your back pocket the next time you upset your mother-in-law. Just tell her at least you didn't work with radioactive substances on her property. Luckily for the Dayton Project, leftover lead dioxide, lead-4 oxide, ore from uranium extraction efforts contained polonium. Unluckily for the Dayton Project, that ore contained the polonium at about 250 micrograms per metric ton of ore. To put that in perspective, the Fort Knox strip mine outside Fairbanks, Alaska keeps profitable by mining gold at the around 400 milligram per ton ore level. That meant that the polonium in the Dayton Project was only about 1,000 times less concentrated than that. To get that really not concentrated polonium out of the lead dioxide ore, the first process was basically just dissolving the lead-4 oxide in hydrochloric acid and then depositing the polonium on nickel or copper sheets. This was not the best. Next, they thought they could just roast the ever-loving you-know-what out of the ore and the polonium would just evaporate out. So really lots of heat. Because having a radioactive substance isn't enough for occupational safety, that radioactive substance now needs to be a freaking gas. Also, the lead-4 oxide just turned into terrible slag before the polonium would come out. So, to fix that, they just hit it with phosphoric acid and turned the ore into lead-2-phosphate. Then the polonium would come out if you blasted it to a high enough temperature. Surprise, surprise, this process had some troubles and was also not the best way to get at the polonium. No, that best solution was to react the lead-4 oxide with a combination of nitric acid and hydrogen peroxide, because HCO was just weak sauce. I've never actually seen nitric acid with hydrogen peroxide. It's sort of like a combination aqua regia piranha solution. It's the honey badger of corrosive solvents. It just takes what it wants. Turns out all those chemical processes were just precursors to discovering we could just blast bismuth with neutrons. The reaction here is bismuth-209 capturing a neutron and becoming bismuth-210. Bismuth-210 then, just looking to see if anybody would answer, goes through a beta decay, creating an electron neutrino, and you got it, polonium-210. Nuclear chemistry, baby. It just never gets old. Turns out bismuth-209 is not technically stable as it wants to alpha decay. That said, it's the most stable of the alpha emitters, having a half-life of roughly 1 billion times the estimated age of the universe. While this reaction looks great on paper, in real life it wasn't so easy. Bismuth wasn't the problem, though. It was antimony. Any residual antimony in the reactor, Sb-123 most likely, would capture a neutron and turn into Sb-124, which is very radioactive. Lots of gamma rays in that one, which is no good for a bomb. Therefore, the bismuth used in the polonium initiator synthesis would have to be really pure. Let's take a look at the polonium purification process. This comes from a great section of Critical Assembly, so I'm just paraphrasing here. After you irradiate your bismuth-210, you get polonium-210 and a bunch of other junk. To get rid of that, you start by heating everything and melting it and then dispersing in water. Then you dissolve in aqua regia and denitrate with formaldehyde. Then you concentrate your polonium by adding solid bismuth powder, 150 mesh. This carries and precipitates out the polonium so you can decant off all the liquid that you don't want. Then you dissolve everything again in aqua regia and denitrate with formaldehyde. At this point, it becomes a choose-your-own-adventure point, where we can either do the tellurium process or we can do the bismuth super scrub process. Not sure why it was called super scrub. Anywho, in the tellurium process, you react with telluric acid, which grabs the polonium and carries it in a precipitate, after you reduce it with tin 2 chloride. In the bismuth super scrub, the bismuth does basically the same thing, except it acts as both the carrier and the reductant. At any rate, once you're done, you have a combination tellurium polonium or bismuth polonium solid that you need to purify. And to do that, you electrodeposit the polonium onto platinum. And that gives you your beautiful polonium-210 that you can use for your Fat Man initiator. This process was only about 50 times more effective than any of the chemical processes and didn't require ludicrous combinations of highly dangerous reagents. But hey, sometimes science is nonlinear. Had we known all that from the start, this discussion wouldn't have been this much fun, right? Final note on polonium synthesis. People who worked with polonium had to have weekly urine tests to check for it in their blood, and when they clocked out, they had to wash their hands first in dilute HCl, then dilute Clorox, then wash with soap. How's that for some cleanliness? The reason is that polonium has a really bad habit of moving. Like, literally, if you put a piece of polonium in a box and come back, the entire inside of the box will be deposited with polonium. The problem is that polonium's melting point is 962 C, and it isn't particularly volatile, so it's not like the polonium is subliming. We still don't have a great handle on why this happens, but the prevailing theory is that the alpha emission from polonium-210 is so strong that it literally blows off pieces of itself when it decays. Alright, let's look at our final design. This bad boy was called the Urchin and was a 7-gram monster neutron generator. Basically, a small beryllium sphere was surrounded by a larger beryllium shell, and polonium was sandwiched in the middle. Two things here though. Both the outside of the sphere and the inside of the shell were coated in nickel and gold to prevent those pesky alpha particles from the polonium from starting off the neutron chain reaction too quickly, being that it was surrounded by, a giant ball of plutonium. Second, the inside of the shell had wedges machined in it to promote better mixing when the core collapsed. In summary, polonium beryllium initiator. When the core compresses, the polonium spits out alpha particles, the beryllium reacts with it, it spits out neutrons, a whole lot of them, and that gets your Fat Man implosion bomb going. The final Urchin design was chosen on May 1st, 1945. For such a small piece of the bomb, the initiator was incredibly important. So important that the exact shape and configuration of the Urchin is still classified 75 years later. Heck, the fact that polonium was even in the initiator wasn't declassified until the 60s. Well folks, it's the moment you've all been waiting for. The whole shebang, the big reveal, it's the implosion bomb in full. As you can see, it encompasses everything we've been talking about this episode, and working from the inside out, we have the polonium-beryllium initiator, the plutonium core, the uranium tamper, the boron-10 neutron scavenger, the aluminum pusher, and our 3-part explosive lenses, composed of an inner Comp B core, the explosively lensed and shaped barytol slow explosive, and then another layer of Comp B. Also, don't forget those wonderful EBW exploding Bridgewire detonators. And this is how to make the Fat Man. Time to get a little grab bag in before we go. In order to make Los Alamos' first ski hill, Kistakowski strapped necklaces of plastic-bonded explosive around trees and blew them in half. Kistakowski also taught John von Neumann how to play poker. In the man's own words, quote, "When I came to Los Alamos, I discovered that these people didn't know how to play poker and offered to teach them. At the end of the evening, they got annoyed occasionally when we added up all the chips. I used to point out that if they had tried to learn violin playing, it would cost them even more per hour. Unfortunately, before the end of the war, these great theoretical minds caught on to poker and the evening's accounts became less attractive from my point of view." End quote. One more story about Kistakowski. After VJ Day, Kistakowski got totally soused. He actually said soused in the interview, and blew up 1,000 pounds of TNT for fun on a dare, while being almost blackout drunk. Legendary. The parties at Los Alamos used grain alcohol, almost certainly ethanol water at the azeotrope of 190 proof. Good stuff if you can get it. The first time he tried square dancing, Enrico Fermi was part of the head couple. Said somebody who watched him, quote, "He danced with his brains instead of his feet," end quote. My wife will tell you the exact same thing about my dancing. I take that to mean I'm pretty similar to Enrico Fermi. Another Fermi story about fishing, quote, "He had tackle different from what anyone else used for trout fishing, and he developed theories about the way fish should behave. When these were not substantiated by experiment, he showed an obstinacy that would have been ruinous in science," end quote. And that, my friends, is how to make an atomic bomb. I hope I've given you a glimpse of the huge amount of work it took in creating techniques and devices that had never previously existed. At any rate, we now had 2 bomb designs that were basically ready for deployment. But that's for then, and this is for now. See you next time.
Now I am become death, the destroyer of worlds.